This is your presenter Asloob Mudassar, and I am presenting slide number 86 of the course on laser physics. Question is, assume that a resonator consists of two mirrors with infinite apertures. The propagation of array for one round trip between the two mirrors is described by an ABCD matrix. Determine the propagation kernel for the round trip journey in terms of the parameters of the ABCD matrix. Also establish the stability condition. You see that in the previous question, in one of the previous slides, we have addressed a similar problem where we have mentioned the stability of a resonator and we have given some conditions. But there the aperture has limited size. Now here we are assuming infinite apertures. So let's answer this question. The answer is, consider a general two-mirror resonator with infinite apertures. That is, A1 goes to infinity, A2 goes to infinity. The plane P in front of the first mirror is located at Z is equal to 0, where the initial field under paraxial approximation is represented by U of x1, y1, 0. That is E prime of x1, y1, 0 is equal to U of x1, y1 and 0. So let me explain the diagram that we are using. So figure number 1, a typical two-mirror resonator with infinite apertures. So you see that here we have the apertures of the left mirror equal to 2a, and here at the bottom we have set that a1 goes to infinity. Similarly, the spherical mirror 2 has a dimensions of 2a2, and we are now assuming that a2 now goes to infinity. So it means that we are effectively contributing, we are effectively understanding that the dimensions of the spherical mirror 1 and the spherical mirror 2 are of infinite extent. We have drawn a P just in front of the mirror 1. Because the ABCD calculation, when we want to talk about the ABCD matrix calculation, we have to consider only plane surfaces. So we are considering a plane P in front of the spherical mirror M1, and similarly we shall also consider another plane parallel to the plane P in front of the spherical mirror 2, but I have not shown that one in the diagram. The radii of curvature of the surface 1 and the surface 2 are R1 and R2. You will see that a ray labeled as Q1 will leave the plane P and will move towards the mirror M2. So after the mirror M2, it will be reflected by the mirror M2 and will propagate towards the mirror M1. And again from the mirror M1, the mirror M1 or the plane P, the light is reflected, or the ray is reflected as a variable Q, where Q1 and Q2 are the complex radii of curvature. And you see that we have described Q and Q1 in one of the previous slides. Maybe for example, for you to understand this lecture fully, you need to understand the lecture number given in 85, 84, 85, etc. So consult those slides first so that you can have enough background knowledge to understand this lecture. So Q1 and Q2 are the complex radii of curvature, and R1 and R2 are the real radii of curvature of the two surfaces, and capital L is the separation between them. So this is a real cavity or a real resonator. And you see that I have mentioned that the field at the point P, that is the initial field at the point P, is regarded as U of x1, y1, 0. Because we are assuming that the spherical mirror 1 is located at a plane, at an xy plane having coordinates x1 and y1. And the mirror M2 is located at a location having a coordinate x and y. So the first mirror or the plane P are located at z is equal to 0, and the second mirror is located at z is equal to L. capital L. And for a round trip calculation, we can okay, we shall talk about that one later. But you see that here the field is u of x1, y1 and 0. This 0 means that we are taking z is equal to 0 over here, because we are considering that the plane P is located at z is equal to 0. So we have set up that E prime of x1 y1 0 is equal to u of x1 y1 0, where u is actually the special part of the more general field represented by E prime. So E prime will also take care of the phase factor while propagation, whereas u will be independent of the phase variations. So that is the difference between the two fields. So u prime is a more general field that will also take care of the phase factors, whereas u is only the special part of the field and that will be independent of any phase variation when the beam or the field will travel from one place to another place. Now you see that in order to simplify the calculations, we can represent this diagram, that is the two mirror resonator, in the form of a lens guide geometry equivalent to the geometry shown in figure number 1. And here you can see that it is a lens guide geometry consisting of three lenses, lens 1 and lens 1. On both sides of the lens 2 are identical lenses having aperture 2a1 and 2a1 on either side. Because the light, you see that from the mirror 1, for example, will move towards the mirror 2 and will be reflected back towards the mirror 1. So that's why we have the lens 1 on either on the left of mirror 2, on the left of lens 2, and similarly on the right of lens 2. So we have lens 1 identical lenses on either side of the lens 2 at equal distance equal to capital L. And the apertures of these lenses are the same as the aperture of the mirrors, that is 2a1 is the aperture of lens 1 and 2a2 is the aperture of lens 2. 2a2 is the aperture of the lens 2. The focal length of the lens 1 is given by f1 is equal to r1 by 2, because we have assumed that r1 is the radius of curvature of the first of the mirror m1. So that's why we are using the focal length of this lens to be equal to f1 is equal to r1 by 2. And similarly, we have written down the focal length of the lens 2, which is f2 is equal to r2 by 2, because for the mirror 2 we are assuming that its radius of curvature is r2. And of course the focal length is given by f2 is equal to r2 by 2 for this lens. And you see that at the top of each lens we have set that a1 goes to infinity and a2 also goes to infinity. That is, we have set that these lenses are of infinite extent. So I think that the description of this figure 2, which is a lens guide geometry and which provides an equivalence of the geometry shown in figure 1, the description of figure 2 is complete. Now let u of x, y, z represents the field after one cavity round trip or after one period of the lens guide system. So you see that if you talk about u of x, y, z with respect to this diagram, then it will be a field after one round trip. But if you talk about this figure, which is a lens guide geometry, then you see that u of x, y, z will be a field after one period of lens guide. That is the light that is traveling of the field from lens 1 to lens 1, which forms one period of the lens guide system. And then within the Paraxial approximation we shall write that a field E prime as a function of x, y and 2l is equal to u of x, y 2l multiplied by e to the power minus iota 2kl. This u defined at x, y, 2l is the field at a distance 2l from the lens 1, that is after one period of the lens guide. This is the field, and you know that this field is multiplied by the phase which will be traveled or which will be encountered by the field in traveling from lens 1 to lens 1. from the length 1 on the left hand side to the length 1 on the right hand side, the phase factor is e to the power minus iota into 2kl, where 2l is actually the geometrical distance between from length 1 to length 1. And you know that, as I said earlier, E prime takes care of the field, the spatial part of the field represented by U, and also the phase factor along with that. So E prime is a more general representation of the field, or actually the correct representation of the field, whereas U provides only the spatial part of the field. So having equation 1 explained, let's move forward. The field U as a function of x comma y, 2l is linked to u of x comma y comma 0 through the Hagen-Fresnel Kirchhoff integral as given. So here we are connecting the field at the mirror 1, at the length 1 on the right hand side, which is we have declared as u of x comma y comma 2l, with the same field at the length l, at the length 1 on the left hand side, which will be represented by u of x comma y comma 0. The two fields are connected through the Hagen-Fresnel Kirchhoff integral given in equation number 2. So u of x comma y comma 2l on the left hand side is equal to iota over d times lambda, double integral containing u of x1 y1 0, and then multiplied by e to the power of minus iota k. Within the curly bracket we have a multiplied by x1 square plus y1 square plus capital D multiplied by x square plus y square, and minus 2 x1 x minus 2 y1 y divided by 2 times capital B. And of course integration variables are dx1 and dy1, where a, b, c, d. C is not shown in the matrix because C will not appear in this relationship, but you know that a, b, c, d are actually the matrix representation of the field from the initial plane to the final plane. And this is the relationship in terms of the integral, which we call as Hagen-Fresnel Kirchhoff integral. You know that this is the equation that we have discussed earlier in question number 81.24, that is in slide number 81 and in equation number 24. There we have discussed this integral in detail. If you want to know the detail, you should consult equation number 81.24. Now substituting u of x comma y comma 2l from equation number 2 into equation number 1. So we have this field u of x comma y comma 2l. So from this field from equation number 2 can be inserted into equation number 1 over here. So after making that substitution, we have the field in terms of e prime as a function of x, y, 2l is equal to e to the power minus iota 2kl, and then multiplied by the field field from equation number 2. You see that this is the field that we have written after one round trip, or equivalently for one period of the lens guide, that is the field traveling from the lens 1 on the left hand side to the lens 1 on the right hand side, because the total distance there is 2l from lens 1 on the left hand side to the lens 1 on the right hand side. The total separation is 2l. We have also derived a similar relationship of the e prime function, that is e prime of x comma y comma 2l. We have also obtained a similar relationship which is given over here, and we are comparing the equation number 3 with the equation number 4. And e prime of x comma y comma 2l is equal to e to the power minus iota 2k capital L, and then the double integration over the length L will give you e prime of x1 y1 0, and then of course capital K, which is actually the capital kappa as a function of x comma y and semicolon x1 y1, and the of course integration variables are dx1 and dy1. We have also discussed this equation in terms of the propagation kernel kappa in equation number 83.1. You can also consult for the detail of this equation there. Now if you compare the equation number 3 with the equation number 4, then you can immediately write the propagation kernel kappa, which is given next. So comparing the two integrals will give you the value of a propagation kernel kappa as a function kappa, which is a function of x, y, x1, y1, and that is given by iota over d times lambda e to the power minus iota k, and then we have a into x1 square plus y1 square plus d into x square plus y square minus 2x1 into x minus 2y1 into y divided by 2 times capital B, equation number 5. So you see that this is what we have been asked in question number, in the question, that determine the propagation kernel for the round trip journey in terms of the parameters of the ABCD matrix. So you see that we have answered this question through equation number 5. Next we are going to discuss the stability condition. So the propagation kernel in terms of the matrix elements ABCD has been given in equation number 5. But you know that the parameter of the matrix ABCD, which is the parameter C, is not present. The field given below, regarded as a Hermite Gaussian field, forms the eigen solution of the integral given in 2. So let me show this integral given in equation number 2. The solution of this equation is given in terms of the Hermite Gaussian field. So the Hermite Gaussian field forms the eigen solutions of the integral I have just shown you in equation number 2. And the solution of the field from equation number 2 in terms of the Hermite Gaussian field is given in equation number 6. So u of x comma y comma z is equal to 1 over a plus b divided by q1 whole raised to power 1 plus l plus m, and then multiplied by the two Hermite Gaussian functions hl have an argument of square root of 2 multiplied by x divided by w, and then we have hm Hermite function having the argument as square root of 2 multiplied by y over w, and then we have e to the power minus iota k, and then multiplied by x square plus y square over 2q. This is the field that we have also discussed in equation number 81.26. For the detail you should consult slide number 81 and the equation number 26 there. If this field reproduces itself after one round trip, you see that after one round trip it is required the field is reproduced, because this is the condition that will ensure the stability of the resonator. So if this field, that is this field we are talking about u of x comma y comma z given by equation number 6. So if this field reproduces itself after one round trip, then this may be regarded as the field distribution of the cavity eigenmode. Under this condition, the complex beam parameter q must be equal to its initial value q1 defined at the plane P just in front of the mirror 1. So we can set q1 is equal to q in the relationship, and the relationship between q1 and q is equal to a times q1 plus capital B divided by c times q1 plus capital D. And you know that this relation is what we have addressed for the first time in equation number 81.3. That is equation number 3 of slide number 81. You can consult that equation there. We obtain a quadratic equation in Q as given. So if you replace Q in this, if you replace Q1 by Q in this equation, you will get and simplify the relationship and collect the proper terms. You will get C times Q square plus D minus A multiplied by Q minus B is equal to 0. So this is a quadratic equation in the variable Q. But you know that we have defined Q1 and Q as the complex radii of curvature. So it means that in order to solve this equation, we require that Q must be also complex, for which the discriminant of this equation should be less than equal to 0. So for a Q to be complex, the discriminant of this equation must be negative, that is discriminant is less than 0. and you know that the discriminant is given by d square minus 4ac. So I have taken the value of from this equation. So d minus a whole square minus 4 times c into minus b is less than 0, and the simplified result is given below, that is d square plus a square plus 2 times ad minus 4 times of ad minus bc is less than 0. But you know that for a determinant we have ad minus bc is equal to 1, because the determinant of the ABC matrix, which is ADC, which is AD minus BC, should be equal to 1, because over both lenses, for example in this figure, are in the same medium, or equivalently the two mirrors are in the same medium. So the determinant of the ABC matrix should be equal to 1. So we have written that AD minus BC is equal to 1. So making that substitution there, we have a simplified result that d plus a whole square is less than 4. So dividing both sides by 4, we can write that d plus a divided by 2, the square of the whole of this one is less than 1. So this can also be written as in the form of an inequality, that is minus 1 is less than a plus d divided by 2, which is less than plus 1, as shown in equation number 7. And you know that this is the stability condition, the condition for stability that we have also discussed in one of our previous slides, for example probably the slide number 85. So this is the condition of stable resonator. We can conclude that all the stable resonators with infinite apertures will have modes described by Hermite Gaussian field, which we have discussed for example in this equation. So you see that we have derived the condition for the stable resonator with the apertures of the parameter, with the apertures of the resonant, with the apertures of the resonator elements to be of infinite extent. So this completes our answer. So this is the end of slide number 86.